what do you say to people, not me, of course, but what would you say to people who would say that string theory's fallen on hard times? Whoever. Someone asked me to ask that question.
You know, it's a great question, especially because no doubt some people here are aware that some books were written not too long ago which tried to make a case of that particular sort. And what I would strongly emphasize is that the bread and butter of science and the exciting part about physics is you go forward into the unknown, and sometimes there are very fertile periods when there are huge numbers of breakthroughs and your understanding is just leaping forward. There are other times when the theory surprises you in ways that make you step back and really reevaluate and think about things. Now, a theory falls on hard times when neither of those two things are happening, when it stagnates. And we are nowhere near stagnation. We are in a period where we are reevaluating and trying to take all of the things that have been discovered and find how to best organize them so that we can gain the deepest understanding of this theory. But because there is this progress, this steady progress, we feel the theory is quite healthy, but perhaps going in directions that were unanticipated. If you view it in that light, I think the theory is not fallen on hard times per se. If you view it, has the theory achieved the goals that it has set for itself? No, not yet.
Not yet. I mean, that was part of the problem. There were some pretty lofty goals set in the 1980s that as if made it seem as if by the time you know, you had gray hair, and I was losing mine just to make that the theory would be solved, that we know everything. I mean, there were claims made in the 1980s.
The important thing to know is, as you know, those were not malicious claims, nor were they claims coming from some sense of trying to hype. It was really coming from a place of excitement.
Excitement, I think.
You know, again, you know, during that period, it was so wonderfully exciting. In the 1980s, you know, early 90s, there was this real sense that this is going to take us the final step to the deepest understanding. And look, the well-seasoned researchers knew at that point, calm down, everybody. You know, this may be an interesting development, but it's bound to be hard to get it to conclusion.
One of the ways one can, and I don't know the answer to this particular question, one of the ways you can try and judge you know, how a theory is doing is where students are going. And in fact, on stage once, when we were having a debate, one of my colleagues bemoaned the fact that the good students were going to string theory. And you pointed out rightly, I think, that students vote with their feet. And what's exciting is what students go into. And so it was a good sign that the good students were going to string theory. Is that changing at all? I mean, are there more students doing other things that are harder to get students to work on string theory at all?
No, certainly. I mean, my experience is no. But I have certainly encountered students, and maybe it's because my particular research focus of late has been more at the interface of string theory and cosmology. I tend now to attract students that want to work in that domain, that are not working on pure string theory per se, but trying to use the theory to gain some contact with observational data. But I think that in terms, if you were to do a survey, I think that it's quite similar to what it was years ago in terms of, you know, the most theoretically oriented students see this as an opportunity to make the biggest possible contribution, which of course means the biggest possible risk. That's how science works.
It's risk. Now, I don't want to belabor this, the last question in this regard, but what, if anything, would cause you to stop working on this and work in a new direction?
You know, if you started to work on it, you know,
then you want, that's right.
Just, you know, something must be wrong.
Well, it's, when it snows in Phoenix, I guess. But
no, what would stop me from working on it? I guess
I'm still working at cosmology, but anyway, it doesn't matter. Okay.
Which I'm thrilled by. If, for instance, two things I can imagine, and this is quite possible. Somebody comes along, maybe it's some new student, looks at the theory and says, you guys have missed a fundamental inconsistency, a fundamental mathematical flaw that is absolutely insurmountable. That would be enough to say, okay, we have to let this go. And I should say, that has almost happened periodically in the history of the subject, but people then looked harder and the math actually worked when you...
And by the way, I should say, that's the kind of confidence, that's interesting, because that's the kind of thing that drives you further when you think something's going to be wrong and you find out, boy, the mathematics solves things. As a theoretical physicist, that does give you more confidence that there's something right about the theory.
Yeah, you know, absolutely. I mean, there was this anomaly having to do with, you know, Yang-Mills degrees of freedom, that trace F squared had to be equal to trace R squared, which came to a total... I just want to see if they can type this out.
I see.
Okay, you can, yeah, that's close. Yeah, that's not bad. It's falling off a little bit here. Yeah.
Actually, I think
Now, are we going to get into like some endless loop right here if I actually read what's
yeah,
on
it is. We
on
are.
the screen, what's going on here?
So I'm gonna.
Yeah. Okay. Yes. Yeah. Okay.
Actually, string loops, but
Yeah,
actually,
there we are.
actually, I think the way he wrote the equation down was right. I think he may have discovered something.
There it is. Yeah.
But
But the second thing, back to your question, is if a better theory came along. I mean, what we are constantly doing is we are looking at the landscape of possibilities, and if somebody came along with a newer idea that we're like, wow, that maybe retains some of what we've done in string theory, but takes it to a place that gets rid of a lot of the problems that we were encountering, but that's the kind of thing that would make you drastically shift your focus.
okay, now I hate when people ask me this question, but I'm going to frame it because well, the question is sort of where do you think people often ask where's the next great breakthrough, and I always say if I knew I'd be working on it. So let me just not put it that way. But where do you think the most fruitful direction in string theory is right now that may have the greatest payoff?
Well, I do think that the connection to cosmology has great potential. I mean, if you're going to test this theory, there are two ways. Either you test it in an accelerator, you slam things together, and we can talk about what might happen, or you test it through astronomical observations, making use of the fact that the universe itself, we like to say, is itself a giant particle accelerator because the early universe was very energetic, very hot. Things happened there that might be sensitive to the exotic physics that we're talking about. So potentially the imprint of that exotic physics might still be with us in astronomical data. So that's where my focus has been for a number of years. And look, we've done some calculations that suggest maybe in the microwave background radiation there could be a signal. When we first did the work, it seemed quite exciting to me. As we looked further, it began to feel a little bit fine-tuned and less an absolute consequence of string theory. So who knows, maybe they'll find something, but again, if they don't, it won't rule the theory out. So it doesn't quite reach the level that we want.
But I should say that when I came in, started being a research physicist just a few years earlier than you, it was a similar idea. That's one of the reasons I got involved in cosmology. At the time, it was something called grand unification. The unification of the non-gravitational forces required a great leap, not quite as great a leap as string theory, but still a very great leap from where the experiments were. And it seemed to me that the universe, and that's what makes the universe exciting, one of the things is that because it's growing, at early times it was smaller, hotter, much more energetic. And so at early times, there were energies that you could never achieve on Earth in a terrestrial accelerator that were there. And so the universe is a big particle physics device in a sense. And that's really what got me interested in cosmology early on too.
Sure, if you don't mind, another analogy just to amplify that idea, because I think it's a very potent one. If you have a balloon with no air inside of it, and you have a really fine tip pen, you write a little message on the surface of a balloon, you know, it'll be too small for you to see. But then if I blow air into the balloon, it stretches out my little scribble into something that perhaps you can clearly read. So the idea is that the early universe might be affected by these little tiny strings, if string theory is correct, or even the physics of grand unification in some way. And that little imprint of the exotic physics is too small to be seen, and there was presumably nobody there to see it anyway. But then through 14 billion years of cosmic expansion, the message of string theory, if you will, gets smeared out across the sky like my little scribble on the balloon gets smeared out across the expanding surface. So if you know what to look for, or so this approach suggests, you could see the imprints of exotic physics out there in astronomical data.
And let me say, I mean, while that may or may not be the case, that tradition has worked, and probably I'll show some pictures later today, but we use that. One of the reasons that actually one of the people who recently won the Nobel Prize for discovering small hot spots and cold spots in the microwave background is that we definitely think they do provide a signature of another process that happened very early in the history of the universe. And you'll see pictures of it. So it's a tradition that's a noble one, and whether we'll get to the level you want, no one knows at this point. But let's talk about that. We mentioned it a few times, the inklings of potentially being able to detect some of this stuff. It's because of, I think, and you'll correct me, I'm sure if I'm wrong, that the discovery of brains in some sense has driven to an interesting idea that maybe originally the whole idea of string theory was these extra dimensions were very, very small, and that's the reason you couldn't see them. But another interesting possibility has arisen, and that is that they might not be so small, and they could be invisible because only gravity can detect them, and gravity is very weak. But the fact that they can be larger leads to something interesting. So why don't you go on to that?
Yes, so you're absolutely right. One of the developments from the mid-1990s that we alluded to before, that it's not just strings, it's also membranes and three-dimensional blob-like entities. People came up with the idea that perhaps we actually might be living on one of those entities. And it's hard to picture in the actual 3 dimensions, so a 2-dimensional analogy I think is pretty good. If you imagine, for instance, a loaf of bread, maybe I'll just stop right there with a loaf of bread.
We didn't give you breakfast this morning?
Yeah,
or
no,
what was that?
No, so you have this loaf of bread, and imagine that what we have long thought to be the entire universe is just one slice of bread. So a 2-dimensional version of the real 3-dimensional story. And the idea is that there may be other slices, other brains, that we don't see because all of the ways that we access the world, except for gravity, I'll mention in a moment, are kind of trapped on our slice of bread. The strings can freely move along our slice, but they can't get off of it. So photons, that's how we usually see things. The photons can freely move along our slice, but they can't get off. That's why we're unable to see the other dimensions. But these theories also show that since gravity, it turns out, is associated with a snippet of string in which the ends are tied together into a loop, it's not stuck to the brain. The open strings, of which we are made, are stuck by their endpoints. But when the endpoints come together and yield a little particle of gravity, it can escape, and it can probe into the other dimensions. So the idea is, maybe at the Large Hadron Collider, now imagine there's a collider on this piece of bread. So you've got protons going opposite directions around this collider. They slam into each other, and it's possible, the calculations show it's possible that some of the debris from the collision would be these graviton particles that could fly off of the piece of bread, and we'd notice that by having a little less energy after the collision on our slice than before, because the gravitons would carry away energy with them. So that's one of the exciting possibilities that might happen at the Large Hadron Collider.
It's an exciting remote possibility. There's also something else that's gotten a lot of press. You may be, because it changes the nature of gravity in these extra dimensions, gravity acts a little bit differently in order for these theories to work, you might be able to create kind of black holes that might do something interesting. And that's fascinated people, but it's also caused a lot of public press and concern. So maybe you want to talk about that for a second.
Yeah, you know, when the Large Hadron Collider was doing its initial runs some months ago, I'm sure it was the case with you too, I got so many phone calls
all the time
to be on this or that program, and I was like, wow, physics is really, you know, its stature has risen, but they only cared about this idea of black holes that might be formed in Geneva and sort of eat up Switzerland, and then,
yeah.
Which wouldn't be so bad per se, but then if it went on, you know,
actually, you know, it would have helped the whole financial crisis.
I'm telling you, that's right. Or it's a reasonably good metaphor.
Yeah.
But the idea is a serious one.
Yeah.
And scientists in our community have done calculations. I mean, if you create this little black hole, what would happen? Could it eat up the world around it? And the answer is no. And the calculations, number one, they show, based on fairly well-established physics, that these little tiny black holes would disintegrate in a tiny fraction of a second before they could cause, you know, any trouble at all. But even more so, if you don't think that's a convincing argument, these collisions that we can create at the Large Hadron Collider, however powerful they may seem to us, are very weak compared to collisions that are happening in our atmosphere right now. Cosmic ray particles are slamming into our atmosphere with energies far in excess of anything that we'll be able to achieve at the Large Hadron Collider. So little black holes, if they were going to be created in Geneva, would be created there, and if they're created up in space and they're not causing any problems here, well, we should be fine. Some will come back and say, but hang on a second. You create the black hole up there in space, and it has a speed from the incoming particles. Maybe it just rushes through the Earth before it can create any problems. So the final way to answer that is these kinds of collisions also would happen near neutron stars. And neutron stars are sufficiently powerful that they'd hold on to this little tiny black hole. So if black holes eat things up, we should see neutron stars disappearing, and we don't. So the stability of the universe around us pretty much shows us that there's not a problem.
Yeah, and the other example that's been used is the moon, because it doesn't even have an atmosphere.
Yeah,
they
sure.
slam the fact that the
Right
moon,
into
when
it,
you
yeah.
look up at night, there's a moon. It gives you good confidence that they're probably not there.
What do you do during new moon, though?
Well, that's true.
So half the time you're worried.
Half the time, exactly. You can sleep half the month. Let me ask you before we move on to the last thing, because I want to leave time for questions from other people. This idea of extra dimensions, I mean, it is kind of sexy, the idea that we might create them. And I'm excited about one of my students was one of the people who proposed it, as you know, Raman Sundram, when I taught at Yale. And I like to say I was really happy about it because it got him tenure. But I think it's pretty ugly. What do you think?
I don't find those theories from a mathematical standpoint compelling.
Yeah, okay.
So what we were talking about earlier, you're guided by mathematical aesthetic at times, and I don't find that these fit into that.
They don't fit into string theory very easily, do they? I mean, we don't talk about it. I mean, it's just they seem contrived to me, and I just wondered whether you agree.
I agree with that. The only hesitation I have is, when something's right, we somehow have the ability to go back and modify our aesthetic. That's what I'm unsure about.
And now that's, actually that leads it to the nice segue to the last thing I want to talk about briefly. Because one of the things that I wish more people understood, especially I was down in Texas recently talking at the school board there, that the universe is the way it is, whether we like it or not. and if more people could just get used to that idea, that it's nature that tells us how to behave, not us telling nature, it'd be an interesting thing. So it is absolutely true. Many things have seemed ugly. Black holes seemed ugly. So, but then once you realize that might happen, quantum mechanics, all these things seem weird, and we have to adjust our minds to understand them because, like it or not, that's the way nature works. And so maybe in the last 2 minutes, because I want to leave 6 or 7 minutes at least for questions, both you and I spend a lot of time trying to communicate, and I want maybe, and we just did a little TV program the other day talking about that. Maybe you want to elaborate on why you think that's so important.
Well, I think there are a number of reasons that I give when I'm asked questions like that. And sort of depending on the setting, one or another answer I think is most powerful. On the one hand, I truly believe, and I know you do too, that all of the issues and opportunities that we face going forward, the fundamental ones are scientific at their core, right? I mean, the opportunities with stem cells, the challenges with climate change, the possibilities with nanotechnology and human space travel. I mean, all of these things are fundamentally scientific and alternate energy. So you need to have a public that's at least willing to engage with the ideas so that we are making the decision. It's not a decision that's being made on high and basically being presented to us. So I think...
in fact, I would argue that a healthy democracy depends on that, not just in the public, but the legislators as well. If you make decisions in the absence of data, then they're generally not good decisions.
Yeah,
as we've learned in the last 8 years.
So I mean, I agree with that fully, but if you were to really ask me why I do what I do, why I take time out of research, to spend time popularizing science, and there is a huge opportunity cost, right?
Yeah,
I used to think that there wasn't,
but there
and
is.
that was when I wasn't married and I had no kids, right? So what I would do is I would do the writing at night, and I do physics during the day, and it simply meant I was watching less television or reading less books or things like that. But that's no longer the case. So there's a real opportunity cost, and the reason in my heart of hearts why I do it is not because of the issue that we just mentioned. It's important, but I do it because when I see a kid open up his or her eyes and say, "Oh my God, this is spectacular," it feels great.
I agree.
And that's why I do it.
No, in fact, and for me, it's precisely comes down to the same thing. It was a gift given to me. I read Isaac Asimov. I read George Gamow. I read Albert Einstein because he used to write popular books too. And for me, that's what turned me on. And so when I write a book and I see a kid, and enough of them are old enough now that some of them say I became a physicist because it's just
exactly.
Okay. Well, enough of that. Let's go to the audience and feel free to come and ask some questions. So I can't. Thank you.
Thank you.
No, we'll just have to save that. Any? Oh, good. House lights are up so I can see now. Any questions? I guess, are you at the microphone? Why don't you begin?
Yes. Hello?
You're
Hello?
on. Yeah, we can hear you.
Yes. With the Large Hadron Collider being able to possibly create energy densities that will be in the range that the Higgs boson is predicted to be in, would it be more exciting for you for the Higgs boson to be detected or not detected?
Well, I think it's a great question. Just to amplify it, so one of the reasons for building the Large Hadron Collider was and is to find a particle that we in the community of physicists have assumed exists for the last, I don't know, 25, 30 years, if not longer. But as yet we have not found it. It's the one missing piece of the so-called standard model of particle physics. So, you know, if it is found, it will be kind of bittersweet, I think, because it will show us that these mathematical ideas led to a correct insight about nature, and it will complete one particular chapter in our exploration of the fundamental constituents of matter. On the other hand, it'll be kind of sad, because when you close a chapter and you move on, you know, there's this sense of departure, this sense of, you know, it almost would be more exciting if we don't find it, because there'd be the wonderful challenge to figure out what is going on.
Don't you think for a lot of physicists the biggest nightmare in some sense is that we find it and nothing else?
Yes, for the Large Hadron Collider, absolutely. If you find exactly what you were looking for and nothing else, it's hard for you to use that as a springboard for the next step. It's
As
also,
I say, we don't want to be right. I mean, we need the guidance to tell us whether any of these ideas that are coming up in theoretical physics are actually fruitful.
Yeah, I mean, the biggest nightmare is to find absolutely nothing, because we would find that exciting, but it'd be hard to convince the powers that be.
Hey, we found nothing. Isn't that great? You know.
So.
But some of the biggest experiments in the history of physics have found nothing and been very significant, although they weren't funded by the government at the time. Yeah, yes.
So I have a third grader and a sixth grader, and they're going through some standardized testing now, but it doesn't include anything on science. I was wondering, as you talk to legislators and others in the government, what is the feedback you're hearing? Because, you know, science is really important, and I really don't see a whole lot of educational emphasis on it.
You want me? Okay. Well, it is a problem. It is a huge problem, I think, and there are two sides to the problem. There are a lot of educators, or at least school board members, who are really afraid that our kids will learn science. I really mean that. Who are afraid that our kids will learn science and somehow lose their faith, and in fact, one of the great things that's happened this year politically is that at a federal level, we now have the present administration has said we believe in scientific integrity and we're going to only appoint people to boards who have the proper credentials. And I've recently argued, although to deaf ears, I think that we should do the same in school boards. That people should actually have some credentials who are going to make the decisions. But the other issue that I know Brian I've talked about this, and I know Brian feels strongly about it too, is that the other problem is we tend to turn off a lot of kids from science because, for a number of reasons, one of the big problems, at least at the public school level, and it's terrifying to realize, is that in this country, in public schools, most of the middle school science teachers in this country certainly don't have degrees in science. And if you're not comfortable in teaching science, you tend to teach a bunch of facts. But as Brian, and you've talked eloquently about this, I know, it's not the facts that make science interesting. It's the process. It's the excitement. You know, when we're talking about this or string theory or whatever, that's what gets kids excited. And it's kind of sad that we instill this rote facts or require kids to learn these things and not at the same time introduce some of the exciting things that are happening at the forefront. But I think you can only do that if you have some comfort level. If you have some comfort level to depart from the curriculum, or at least included it in the curriculum. And I think that's a problem we have, and that's why the National Academy of Sciences has argued and I firmly believe we should be not only paying teachers more, but recruiting a lot more teachers to teach science who are comfortable with teaching science, and it's only that way that we'll overcome the problem, but it's going to be very hard. I don't know whether you want to add anything else.
Yeah, that captures it well, I think. Yeah.
Okay. Okay, it's all right.
Hi, you described this theory as requiring extra dimensions, and there's also been a radical effort to reconcile quantum and relativity by removing a dimension, specifically the dimension of time. Are any of these timeless models compatible with string theory, and is this an active area of research, or has it kind of been abandoned?
Well, the approach that you're referring to is one that is not as exotic as string theory. It really starts with the basic principles of quantum mechanics and applies them to Einstein's equations as best we can without really introducing anything new. And one of the features that emerges is that time does disappear from the equation, so-called Wheeler-DeWitt equation. And you know, string theory has enough flexibility with our current understanding that it can embrace these ideas, but in no way would I say that string theory leads us to this particular way of thinking about quantum gravity or the early universe. So I'd say it's really up in the air as to how these quantum theories that involve gravity deal with time. In fact, if you were to ask me what the next major breakthrough would be, I would say it's coming to a firmer understanding of what time is in these theories, where it comes from. Is it fundamental? Is it built up from something more basic? And what does that tell us about the fundamental ingredients of the world? So that, I think, is a big frontier area.
Okay, well, I think actually, given the time, that, forgive the pun, that's probably a good time to stop. And before I thank you, I just want to say, I know a lot of you, there are books being sold outside. We're not actually having book signings, and we will hope that many of the people here have written books, and we will try and get a number of them signed, pre-signed for you to buy. We meant to do that this morning, but things didn't work. But we want to really break because we want to have some time for people to have a relaxation before the exciting afternoon session. I want to thank all the speakers this morning. You made it so great. But it's true. They were all great. I do want to particularly thank Brian, not only for having the guts to trust coming out to be interviewed by me, but also there are very few people who I think I would feel comfortable enough to know that we could have such a conversation, and it would be, I hope, of interest to you. So thanks a lot, Brian.
Thank you. Thanks.